Hello everyone, and thanks for watching my videos. In this video today, we're going to be looking into measure the pH of acid and how can we determine their pH and their behavior. So without further ado, here is the video and I hope you enjoy it. Thank you.
So what you see here is a summary of the calculations. So pH is minus log the hydronium ion concentration. The hydronium ion concentration can be determined from this equation by taking 10 to the power. So negative will be in the other side, and taking 10 to the power, cancel the log with 10 to the power, and that become hydronium ion equal 10 to negative pH. You can also calculate the hydronium ion using, again, the hydroxyl ion concentration, or you can calculate the hydroxyl ion using the hydronium ion concentration. Or you can use the general equation that relate the pKw to the pH to the pOH. I want to show you a trend here. Every time you take minus log, that is a B. So B here is an operator in chemistry. This B here, this letter B is an operator in chemistry. Every time you take, say, Bx, that means minus log x. BKa mean minus log Ka. BKB minus log KB, BKW minus log KW. So this is a mathematical operator. That mathematical operator means you're taking minus log that particular, whatever that value is. If this is H, then it's minus log the hydronium ion concentration. If this is BOH, then it's minus log hydroxyl ion concentration. If this is BKW, then it's minus log KW. If it's BKA, then it's minus log KA. If it's BKB, minus log KB. So this is the meaning of B, H, BOH, BKW, BKA, BKB. So BKW is 14. Minus log 1 to negative 14 is 14. Minus log the hydronium ion is BH. Minus log the hydroxyl ion is BOH. So this here relate the BH to the BOH, which equal 14. So 14 equal BH plus BOH. This is going to become very important, this equation, when you are dealing with a base. And I'm going to show you why it's important to refer to this equation when you are dealing with a base. The first substance is a strong acid. If you are provided with a strong acid, if the question is saying you have HCl, or you have HBr, or you have HI, you have nitric acid, sulfuric acid, perchloric acid. So again, you have this chloric acid. This is perchloric, this is chloric acid. So you have these chemicals, you know. All right, so what it mean, the term strong acid? It means strong electrolyte. Strong acid is an acid that completely dissolves in water and is thus a strong electrolyte. A strong electrolyte will 100% dissociate. So you have a one-way arrow. That one-way arrow indicates 100% dissociation. So say the acid concentration is 0.1 molar. Say HCl has concentration of 0.1 molar. Say HBr has a concentration of 0.1 molar. Say nitric acid has a concentration of 0.1 molar. What will be the pH of that acid? To calculate the pH, you need the hydronium ion concentration, because remember, the hydronium ion pH is minus log the hydronium ion concentration. So all what we need to do here is basically, since this is 100% dissociation, if this is 0.1 molar, then you're going to produce 0.1 molar of hydronium ion and 0.1 molar of A negative. This is the concentration you have. Because you're using the solution stoichiometry, right? The concentration is basically you have, this is 1 mole, and this is 1 mole. So if this is 0.1 molar, you're producing 0.1 molar of hydronium ion and 0.1 molar of, again, A negative. All right? So do we know the hydrogen ion concentration? Answer is yes, we know the hydrogen ion concentration, which is 0.1 molar. And from here, BH will equal minus log the hydronium ion concentration, which is minus log 0.1. All right? So from here, we got the BH1. So this is a straightforward. The calculation here is a much easier, straightforward, because we have 100% dissociation. Weak acid. There's a whole different chemistry here. Whole different chemistry. Why? Because you said the word weak. What's a weak mean? Mean partially dissociate in water. What's a partial dissociation mean? Chemical equilibrium. Right now, we have a chemical equilibrium. And that chemical equilibrium is involving HA dissociating to hydronium ion and A negative. So I no longer can say I have 0.1 molar of HA, it's going to produce 0.1 molar of hydronium ion. Why I cannot claim 0.1 molar of hydronium ion? Because of this. This is, again, showing you that some of it is dissociated and some of it is not. This one here, all of it is gone. This one way indicate all of these is gone to 0.1 molar of hydronium ion and 0.1 molar of A negative. So how can you obtain the equilibrium concentration? How can you obtain this hydronium ion concentration? The only way to obtain this is to run the ICE table. The ICE table. You're going to use this a lot beyond 102, especially in quantitative analysis. So the ICE, what's an ICE table? This is just the initial, change, and equilibrium. So the ICE table stands for initial, change, and equilibrium. Initial concentration, which is given to you. Initially, you don't have any of this, right? There is no initially, you don't have any dissociation yet. So this is 0 and 0. Now you have a dissociation of X. You lost X from here, from HA. This X converted to product. We cannot claim that X to be 0.1. Why cannot claim X to be 0.1? Because I don't have 100%. In here, that was easy. There was no X. There was no X here because it's 100%. This one here is not 100% dissociation. So what would be the equilibrium concentration? What would be the remaining after the dissociation of X? Will be 0.1 minus X. What will be the remaining after X? Will be X, right? Because you start with 0. So this is your equilibrium, X and X. So we have the equilibrium concentration. The equilibrium concentration of HA is 0.1 minus X. The equilibrium concentration of X is, of hydronium ion is X. The equilibrium concentration of A negative is X. Here are some of the weak acids. And if you look at them, you're familiar with them, they all have this carboxylic group, COOH. These are acids that we are familiar with. This is formic acid. This is lactic acid, which is produced by metabolic products. And this is acetic acid, which is, we use, again, small percentage of that in vinegar. So vinegar contains 6% of this acetic acid. So the vinegar that we use at home to add to the salads and things like that is, again, acid. But it's a very weak acid because we only use 6%. And then we have carbonic acid, which is, again, as you can see, this is basically carbonated soda and or carbon dioxide and water. You'll get carbonic acid. So as you can see, these are weak acids, which mean they're going to follow this trend. They're going to dissociate through this trend. All right. So how can you do the calculation? So now here is the problem. Here what we have. Here is the ICE table. Now how to go from this ICE table to the calculation? What we need to know here is this equilibrium, and we already know this equilibrium concentration. We know that basically the equilibrium constant is going to be called acid ionization constant or acid dissociation constant. And this acid dissociation constant is equal product divided by reactant. Does not include the water because water is pure liquid. So it's hydronium ion concentration times A negative concentration divided by HA concentration. Do I have this concentration at equilibrium? Yes, I have this at equilibrium. 0.1 minus X, this is HA. X is hydronium ion, X is A negative. So here is the product divided by reactant. We have not covered anything new, except we are applying the principle of chemical equilibrium to the dissociation of acid, to the acid dissociation. And we call it right now acid dissociation constant. So the equilibrium constant now has a specific name, and that specific name is applied to a specific process, which is the acid dissociation process. Now, do we know what's hydronium ion, X? Do you know what's A negative, X? Do I know what is HA, 0.1 minus X? Now, in quantitative analysis, it's not going to give you this simplified form. In quantitative analysis, you're going to use this form, and you're going to use quadratic equation. You're going to set up a quadratic equation where you're going to have x squared and you're going to have x. So you're going to have a quadratic equation with the form ax squared plus bx plus c equals 0, and you're going to solve for quadratic function, and you're going to get x. For us here as 102, we're not going to use the quadratic equation. So for us here, we're going to always ignore this x. So when we ignore this x, then you're going to end up with 0.1. Why are we going to ignore this x? Because this Ka is going to be always very small value. You're going to have a Ka of 10 negative 5, 10 negative 6, 10 negative 4. So that's going to be a small value that you can ignore this x. So this x will be very small compared to the 0.1. And we're always going to ignore this x. That's why the x disappear here and you get with 0.1. So this way, you no longer have to worry about quadratic equation, because now all what you have is a cubic function. You have just a square function, and this square function, you're going to basically solve for x. So x squared. So here, x times x will give you x squared, and that will equal 0.1 times k. By cross multiplying, x squared equal 0.1 times ka. Remember, this ka is a constant. So this equation right now has two unknown. Has x, which is the hydrogen ion concentration. Remember, this is x, which is the hydrogen ion concentration. And Ka, which is the equilibrium constant or the acid dissociation constant for the acid, which is going to be given to you. So this will be given to you. So if this is given, you can get Ka. If Ka is given, you can get x. If I give you the Ka, you take the square root of this side. By taking the square root of this side, you will get x. Once you get x, what is x? X is the hydronium ion. So did we get our BH? Yes, minus log that will be the BH. So this is the calculation. Look at just how complex this is. Going from strong acid to just the term weak. Just by adding the term weak to acid, the calculation become more complex, and again involving square function or even a quadratic function beyond 102. So beyond 102, you will have to do it through quadratic function. All right, so the BH will equal minus log hydronium ion. That's for a strong acid, and it's immediately you get the BH. For a weak acid, you have to do multiple steps where you conduct the ice table. By constructing the ice table, you will use the acid dissociation constant, and you get X, and from X, you get the BH. So let's demonstrate this with an example, because I want to make sure that everything is clear here. So here is the example. Calculate the BH of 0.1 molar HCN solution at 25 degrees Celsius. Ka is 1.4 10 negative 9. So clearly that's a weak acid. Ka is 1.4 10 negative 9. And it's HCN, which is another weak acid that you should be familiar with from 101. But if you're not familiar with, HCN is a weak acid, hydrogen cyanide. So do we have the initial concentration? Yes. Do we have the Ka? Yes. So here is the ice table. Initial concentration 0.1, 0 and 0. We lost X, we gain X. Your equilibrium is 0.1 minus X, and X, and here is your equilibrium dissociation of the HCN. Here is Ka, so we know Ka already. So in this case, Ka is given 1.4 to negative 9. X times X divided by 0.1 minus X. And that will give us X squared divided by 0.1. We ignore the X. Look at this. This is very small. If this is very small, X will be very small. So you can ignore X in terms of 0.1. Why you cannot ignore X in a multiplication? You never ignore X in a multiplication. You can only ignore in addition or subtraction. You cannot ignore X in multiplication or a division. All right, so X will equal hydronium ion, which is equal from this calculation 1.18 10 negative 5. So did we calculate the hydronium ion concentration? Yes. So are we ready to calculate the BH? Yes, because you got the hydronium ion. The whole idea about the calculations here is to calculate the hydronium ion concentration. If you got the hydronium ion concentration, all what you need is take minus log that.